welcome the first speaker. The talk is EasyBC, a cryptographic specification language for security analysis of block ciphers against differential cryptanalysis from Busan. Take it away, thank you.
Okay. Ladies and gentlemen, good afternoon. My name is Pu Sun, a PhD student from ShanghaiTech University in China, supervised by Professor Fu Song. Now let's begin. Firstly, a block cipher is a symmetric cryptographic technique.
Your microphone is still on.
Wait. Now?
Yes. Don't touch the mic yourself, sorry.
Okay.
It's very fragile, you're going to be careful. Sorry.
How about now?
Yes.
Okay. A block cipher is a symmetric cryptographic technique that uses the same key to encrypt and decrypt data in fixed size blocks. And with the application scenario of block ciphers are expanding, its security against the various cryptanalysis has attracted research attention, especially for the differential cryptanalysis. And the differential cryptanalysis is a algorithmic-level attack against block ciphers, which recover the key by analyzing the effect of the differential propagation. And the key is more likely to be recovered by using the optimal differential characters, which corresponding the maximum embedded differential character probability, short for max EDCP, right? Here is an example. For a given encryption process of a block cipher, the attackers can generate and select their optimal differential character probabilities by using a large amount of input pairs of the block cipher. Then based on the selected optimal differential characters, some bits of keys can be recovered by utilizing the output difference of the cipher and the output difference of the S box, like shown in this figure. And the security of block ciphers can be evaluated by the max EDCP, which can also be deduced by the minimum number of active S boxes. Well, the core of security analysis is how to calculate the minimum number of active S boxes or the max EDCP. Here are some techniques that were proposed to solve this problem. For example, bound and branching searching and mixed integer linear programming, SAT, SMT, and so on. However, this technique is suffering some problems: poor generality, insufficient automation, and user unfriendly. Our goal is to develop a generic and automatic approach for evaluating the security of block ciphers against the differential cryptanalysis based on their domain-specific language. Well, the designing of a domain-specific language is based on analyzing the block ciphers and their implementations. For example, from the code fragment of block cipher 1, we can extract two features. The first one is that the value types and the value range can be fixed. And the second one is that some cryptographic-specific operation can be simplified. And then by analyzing other commonly used block ciphers and their implementations, we can extract two more features. The third one is that the function type can be fixed either. And the last one is that any given implementation of block ciphers must be terminated for any given input. Then based on the extracted different language construction, we design our domain-specific language named EasyBC. For example, for the EasyBC, it can use only one line code to implement the substitution process. Compared with the aforementioned example, it provides a more conscious way to implement block ciphers. And the EasyBC provides cryptographic-specific types to facilitate the implementation of block ciphers, such as P-box, S-box, matrix, vector products, and so on. And it's fully specified by formal grammar together with typing rules and operational semantics, which enables further automatic analysis. And we also provide implementations of commonly used block ciphers for user learning. Then based on the EasyBC, a generic and automatic approach was proposed. It takes the EasyBC implementation of block ciphers as input, and after the pre-processing and type checking, one of three approaches will be selected to generate the corresponding MILP model. After that, solver will automatically involved to solve the corresponding models and obtaining their final results. That is to say, the minimum number of active S-boxes or the max EDCP. And the pre-processing processes range for loops elimination, constant folding, constant propagation elimination, and data code elimination. And type checking ensures that the given input is legal, and it also provides some extra information used for subsequent security analysis. After that, one of 3 approaches will be selected to generate a corresponding MILP model, right? The first one is the worldwide approach. It suits for the program where types of all variables has fixed bit size, and each entry of an array will be modeled by a corresponding Boolean variable, where the Boolean variable takes a value of 1 indicated that entry had the difference. And each statement will be modeled by a set of integer linear constraints over the Boolean variables. Besides, each S-box is associated with a unique Boolean variable to indicate whether the S-box is active. Before the specific generation, we give 2 examples of the integer linear constraint set. The left one is the inclusive OR, and the right one is for the linear transformation. And from 2 sets, we can observe that this set is both based on the branch number, where the branch number indicates the range of sum of input difference and output difference. Then based on the aforementioned code fragment of block cipher 1, we show how to generate the specific integer linear constraint. Before that, some information needs to be processed. Like the specific value of S-box extracted from the type checking and pre-processing, we can generate its corresponding differential distribution table of the corresponding S-box, which structures the distribution of the possible differential propagation. And for each expression, we decide its corresponding integer linear constraint set based on its specific operation. If the operator is the substitution via the S-box, then this constraint will be generated, while the operator of this constraint is based on whether the S-box is injective. If the operator is inclusive OR, then the aforementioned integer linear constraint set will be generated to model this expression. All this generation process maintains mapping from each difference of variables to the corresponding Boolean variable. And all the integer linear constraints will be generated by traversing all statements and expressions. Besides, an extra integer linear constraint will be generated to ensure that the input difference of the block cipher is non-zero. And the target function of the overall model is to minimize the sum of all the Boolean variables corresponding to the input differences of all S-box. Then by constructing the overall mixed integer linear programming model, we can use the solver to solve it and obtain the minimum number of active S-boxes, right? Besides, based on the max differential probability of the S-box, which can obtained by the constructed DDT, right? We can determine the security bound of the corresponding block cipher. In some cases, the constructed MILP model may be too large to solve. Hence, we can evaluate the security by using a cipher with small round number. Specifically for the block cipher 2, we had its max differential probability is 2 to negative quadratic, and it has block size 16.4, and then we can deduce that when the number of minimum number of active S-box is at least 32, it is security enough. By using the solver to solve the corresponding constructed models, we got the result as shown in this table. And from the table, we can know that when the round number is 15, you can show that the 1 is security enough, since 32 is larger than or equal to 32. Worldwide approach involves fewer variable and fewer constraints. However, it's only suited for some specific structures. Well, it's not suited for the bit-oriented structure block ciphers like present. Thus, we present bitwise approaches to address this problem. For example, for the modeling of X-boxes, which is modeled by only one constraint in worldwide approach, well, it's integer linear constraint set consists 3 parts. The first part is they're based on their branch number, as we mentioned before. And the second one is for associating a unique Boolean variable bx to their corresponding S box to indicate whether the S box is active or not, right? And the last part is the specific modeling for the differential propagation in the corresponding DDT. Bitwise approach is more fine-grained and has wide applicability. However, the abundant is maybe not sufficient enough in some cases. For example, gift curve, right? Then the extended bitwise approach is proposed to address this situation, which use some extra Boolean variables to model or encode the specific probability of the differential propagation. Here is the modeling of the S boxes, which constitutes two parts of the integer linear constraint set. The first one is also based on the branch number, and the second one is the specific modeling of DDT, right? And each inequality, we use 3 extra Boolean variables to encode its specific probability. Extended bitwise approach may be less efficient, but it's more accurate than the wordwise approach and the bitwise approach. To evaluate our approach, we select 23 cryptographic premise, and we first evaluate its premise. We compare the line of code of EasyBC implementation with the line of code of C implementation, and from the result we can know that EasyBC provides a non-conscious way to implement block ciphers. We also compare the runtime, and from the result we know that EasyBC is actually applicable. Next, we show 3 of the result of our 3 approaches. The first one is the worldwide approach, then the bitwise approach, and the extended bitwise approach. Where the highlight is show that the bound of resistance against the differential analysis under the certain round. And for the keyless permutation, we only use them to evaluate the performance of our EasyBC and our approaches instead of the security evaluation. And EasyBC is able to effectively handle all realistic block ciphers, and it can prove the resistance of all block ciphers shown in their tables. Note that the resistance of gift curve cannot be proved by bitwise approach, but it can be proved by the extended bitwise approach. And DES is vulnerable to differential cryptographic analysis. Last, we have 3 questions to discuss. The first one is, are there any block ciphers which are unable to implement it in EasyBC? The answer is, if there is a newly designed block ciphers with their operations that are not supported by EasyBC, then EasyBC cannot handle it, right? The second one is how to choose the use of the 3 approaches in practical application. Actually, this is a trade-off question. Worldwide involves fewer constraints and fewer variables. However, it can only suit for some specific structures. And the bitwise approach is more fine-grained and has wider applicability. However, the upper bound of max EDCP updated via the bitwise approach and the worldwide approach may not be sufficient enough in some cases. And the extended bitwise approach is less efficient, but it can obtain a tighter bound of max EDCP. The last one is how to expand the EasyBC. There are 2 perspectives to expand EasyBC. The first one is expand EasyBC to other craft analysis, right? Like linear craft analysis, related key differential craft analysis, and so on. And there are other expanded ways to expand the EasyBC suited for other cryptographic algorithms like stream cipher and so on. Here are the takeaway points. We designed a domain-specific language named EasyBC suited for block ciphers, and we provide a generic and automatic approach for security analysis, and we evaluate them. That's all. Thank you.
Questions? I'll give you my mic.
Thank you for the talk. Maybe I missed the point. What kind of code do you generate? Do you generate assembly code, C implementations? And second question, how does EasyBC compares to other DSL such as Jasmine?
You mean how to compare with the EasyBC with the apprentice?
With Jasmine, which is another language to implement cryptographic implementation to cryptography.
This one? Pardon?
Jasmine is another language to implement cryptography. How does EasyBC compares to Jasmine? And second question, what is the target? What kind of code do you generate? Do you generate C implementations or assembly implementations?
Okay. The EasyBC code is generated based on the specific grammar, right? Then our pre-processing and type checking will generate its corresponding code like a SSA. Then based on this, we can analyze it based on its specific operations and likewise.
Repeat the question. Different voice might have.
Do you want to ask a question again, or do you?
What was the target for the generated code?
Yeah.
What programming language did you generate?
Yeah, we do generate C, C++, something. What was what did the DSL produce? What's its output?
Which language our approach is supported?
Yeah, yeah. When you run EasyBC,
yeah.
What does it produce as output artifacts?
Or output, right?
Yeah.
The output is either security, either results of the security of block ciphers against different cryptanalysis. It's just a report, right? Also, we can run the EasyBC implementation by our interpreter. That's why that's how we can to evaluate the running time of the EasyBC program. Okay.
Any more questions? Let's check my Discord. Okay. Well, there's no more questions. Oh, yeah, right. Okay.
So you start with a cryptographic algorithm written in C or C++. You encode it in EasyBC so that you can then do the security analysis automatically. But how do you know that what you've encoded in EasyBC matches what was in the original C or C++?
Actually, I don't get it, right? Could you pardon?
Sorry?
Could you repeat your question again?
You start with an algorithm written in C or C++.
Yeah.
To do the security analysis, you then re-encode it in EasyBC. How do you know that when you've translated it, that you've translated it accurately, that you have the same thing?
Actually, we don't translate it. We assume that the user will use EasyBC language to implement their block ciphers directly. Instead of using the C or C++, we don't do the translation.
But then, don't you need to turn EasyBC into something that executes efficiently?
Actually, our subsequent security analysis to trains is based on the EasyBC. So only we concern is that the analyzing to trains is based on their design, based on their features of EasyBC to design that. That's why we need a domain-specific language.
Do you want to try rephrasing my question?
I mean, I think given the time, maybe we carry on this discussion in the break afterwards.
Okay.
And thank you for the talk, and let's get set up for the next one.
Okay.